Welcome! This is the first tutorial of a three-part series on how to get started with the gas turbine performance software, GasTurb. The tutorial series provides an introduction to GasTurb's user interface and its most frequently used features. A basic understanding of gas turbine performance calculations is recommended to make best use of the software and follow the tutorials. In this first tutorial, we will learn how to perform simple design calculations in GasTurb. We will first start with an introduction to the GasTurb main window. Then, we will conduct a design point calculation using a turbojet engine. Next, we will look at how to use the GasTurb formula editor and how to visualize the cycle in an HS diagram. Finally, we will use iterations to match a process with predefined target values. Let us start GasTurb now. After starting the software, the GasTurb Welcome window appears. In this window, we select a file from the Recent File list, load a save file, or start a new project by selecting any of the configurations on the right. In this tutorial, we will start with a new project from scratch. To start, we select any of the configurations from the different tabs, like Jet Engines, Turboprops, Gas Turbines, or new in GasTurb 15, Electric and Turboelectric. Let us return to the Jet Engines tab. For the following design point example, we will use the turbojet configuration. We click on the turbojet. For some configurations, a selection between multiple demo datasets is offered. In GasTurb, we always start a new project with demo data containing reasonable inputs for the selected configuration. We will see later in this video how to adapt the inputs. We continue with the configuration without the afterburner. The main window for the turbojet appears. On the right, we see the schematic of the selected configuration. On the left, we can switch between calculation scopes. The basic scope calculates the gas turbine based on simple textbook knowledge, which is especially useful for basic understanding and teaching. The performance scope runs a more detailed gas turbine performance calculation and is the usual operating mode for performance specialists. With the option More, in addition to the cycle, the engine geometry can be determined and component masses can be calculated. It is the most detailed engine design option. In this video, we will use the performance scope. To continue, we have the choice between the design and off-design mode. In this tutorial, we use the design mode, which is always the first step when starting a new project. We will look at the off-design mode in a separate tutorial. The design point input window for the turbojet appears. On the left, the simulation task we wish to conduct can be selected. To conduct a design point simulation, choose the corresponding button. Here, it is by default already selected. The input data is presented in a table on the right. According to the selected branch in the data tree, different input data can be observed and edited. Initially, basic data is selected. The most important input design parameters are listed here. For example, the burner exit temperature or the pressure ratio. Now we click on Ambient Conditions. We can set the Mach number, flight altitude, and temperature deviation from the standard atmosphere to define the inlet conditions of the gas turbine. Alternatively, the ambient pressure and the total pressure and temperature at the engine inlet can be directly specified. Let us click on Stations now. The stations are labeled in accordance with SAE notation. The flow areas at the stations are either derived from a Mach number or input directly. The flow areas influence the calculated static pressures and temperatures but do not affect main cycle parameters like thermal efficiency or thrust. There are several more input options for the secondary air system, the compressor, the turbine, the reheat system, and the nozzle. We will not look at these in detail now, but continue with the design calculation. We leave all input data with the predefined values and click on Design Point to start the design point calculation. When the calculation is completed, the results of the simulation will be displayed. In the summary window, thermodynamic details regarding the states in the stations will be shown, as well as the cycle parameters like thrust or specific fuel consumption. All parameters are abbreviated in accordance with International Standard Nomenclature for performance computer programs. If we wish an explanation of a variable, we can click on the result variable abbreviation and a hint will open. Let us now take a look at the details at the thermodynamic stations. We select the Stations tab. For every station of the gas turbine, all the thermodynamic parameters are listed in the table. The calculated values for the areas can be observed here as well. In off-design simulations, the static pressures and temperatures are calculated based on these values. We may wish to know a cycle property which is not listed on the output page. We can add additional outputs using the gas turb formula editor called Composed Values. To define these composed values, we first return to the input window by clicking Close. We select the Additional button and then click Formulas, which opens the Define Composed Values editor. The Composed Values editor allows us to create additional output values from all input and output quantities. We can even use empirical correlations and more than 50 predefined functions. Let us calculate the kinetic energy of the nozzle exhaust in kilowatts as an example. We click on the first field and select the parameters from the Input-Output menus. First, we click on the Output tab and open Thermodynamic Stations, Station 8. Now, via drag and drop, we can add the mass flow and the velocity to the equation. To check and evaluate the composed value, we click on Value. Let us return to the Design Input window by closing the editor and run the design point calculation again. By clicking on the Additional tab, we can see the calculated composed values. GasTurb allows us to display the calculated work cycle in numerous diagrams directly from the output window. To access the enthalpy-entropy diagram of the cycle, we click on Diagrams HS. The HS diagram of the calculated cycle is displayed. The slider tool allows us to modify an input quantity manually and to observe the change within the displayed diagram. We choose the pressure ratio in the limits 2 to 22. Reduce the slider for a better overview. In order to draw a comparison to the previously calculated cycle configuration, we click on the Freeze button. Using the slider, we can see how the pressure ratio affects the thermodynamic cycle whilst being able to compare the changes to the reference cycle. The other design parameters, the burner exit temperature for example, are kept constant. Let us reset the pressure ratio and return to the output window. Now let us select the Summary tab where we again see the results of the original cycle. The turbine pressure ratio of the calculated cycle is approximately 3.2. This pressure ratio is easily achievable with a single-stage turbine. In fact, a single-stage turbine can work up to a pressure ratio of 4 with acceptable efficiency. A higher compressor ratio would be achievable, which, as we know, might allow to run the turbojet with higher overall efficiency. In order to find the compressor pressure ratio which yields exactly the turbine pressure ratio of 4, we can specify so-called user-defined iterations. For defining an iteration, let us return to the input window by clicking Close. To open the Iterations editor, we select the Additional button and click on Iterations. Each iteration is defined by a variable parameter which is adjusted until a target parameter meets a specified value. We wish to vary the compressor pressure ratio until the turbine pressure ratio is 4. We choose Pressure Ratio from the Variables menu and drag it from the selection tree to the column Variable in the table. Then we define minimum and maximum values. We set a minimum pressure ratio of 10 and a maximum pressure ratio of 50. Afterwards, we choose the turbine pressure ratio from the Targets menu and set the target value to 4. Finally, we click the Activate box in order to include the iteration in the design point calculation. Multiple variables with their corresponding targets may be defined and run simultaneously. Now we close the Iterations editor and rerun the design point calculation. As we can see in the summary window, the target value of the turbine pressure ratio could be achieved and the compressor pressure ratio was increased. A comparison of the previously calculated cycle with the current cycle shows that the higher pressure ratio leads to lower specific fuel consumption. More details are visible when we click the Additional tab and select the Iterations button. The defined iteration is displayed with the number of iteration loops required to converge. Defining multiple iterations may be complex, and this window is especially useful when the iteration does not succeed, for instance when the min and max limits are too narrow. To save our cycle design, we return to the Design Input window. By clicking on the Save button in the Project group on the left side, we write all inputs, including composed value definitions and iterations to the chosen file. The next time we want to work on the model, we can simply select the file from the Recent list in the main window or double-click on the file in the File Explorer. This concludes the first gas turb tutorial. We learned how to calculate a gas turbine cycle and got to know the gas turb formula editor and the iteration function, simple tools that greatly facilitate the gas turbine design process. Enjoy applying them to your design tasks and let us know if there are any questions left. In the following tutorial, we will learn how to perform parametric studies with gas turb, which further facilitate the gas turbine design process.